Hello again. Um, yes, now I'm going to first quickly go over first week's slides. And then, as I said, I'm going to talk about some of these geometric preliminaries that we will be needing if you want to implement the techniques uh, we will be learning in this class. So, computational geometry, we will first start with convex hulls. I already told you that. But the first weeks of slides, I will also use some additional slides by Professor Andy Mirzayan from Department of Electrical Engineering and Computer Science, York University, Canada. So he has a really nice course web page which is still available. There are some lecture notes, some papers about computational geometry. If you're interested, you can also check his website. Uh, as I said, computational geometry involves lots of areas from computer graphics. We will see in chapter 8 an application of ray tracing. We will see application in robotics. In the final chapters, there are applications in geographic information systems, GIS. So it has different applications. And I also told you that we will see incremental algorithms, divide and conquer algorithms, randomized algorithms, the plane sweep technique, and we will learn lots of data structures. Okay, the simplest problem of convex hull problem is again the input is a set of points in this case. So the goal is to find the smallest convex polygon that encloses all of these points. In many geometry problems that are given like this, we need to first think about the problem and do some geometric observations. So one observation here is that if there's a convex polygon that encloses all of these points, the edges of this polygon should be connecting two points already in the set. So what I'm saying is that, so let me just again copy this directly to my whiteboard here. So what I'm saying is that, for example, if this is a convex polygon, okay, there's a convex polygon that encloses all of these points. This is not the smallest convex polygon that encloses these points. If you think about it as an elastic rubber band, you will intuitively, your first observation is going to be the smallest convex hull. Its edges are going to be connecting the points already in the set. So this is a convex polygon, and it will be the smallest one, and which means that finding convex hull simply is the problem of finding a subset of these points that are on the vertices of this convex hull. After you, for example, after you have this observation, you can also have other observations. For example, if a line segment connecting two points is an edge of a convex polygon, then we may have this observation saying that all the other points, if it's an edge of the convex polygon that encloses all the points, all of the points should lay on one side of this edge. For example, this is another line segment connecting two points, but if you just take a look at this line that passed through these 2 points, some of the points are on the left-hand side, some of the points are on the right-hand side, and therefore this cannot be a convex hull edge. So these observations immediately sometimes may lead to an algorithm. For example, an algorithm, by exhaustive searching, I can do this. Look at all the pairs of line segments connecting, every line segment connecting every pair of points in my set, and check whether all of the other remaining points are to one side of this. If this is the case, then it should be a convex hull edge. But this is a very inefficient algorithm. It will have O(n) cube complexity, right? Why O(n) cube? Because there are O(n) square pairs of points, O(n) square line segments to check for every line segment, to check for every other point, n-2 points. There are n-2 points to check whether they're all on the same side of this. All right, so in total, since I have to do this ON step for every one of those n square line segments, I have an ON cube algorithm, which is really inefficient. We will see an algorithm that works in ON log n time. Okay, so which will be much more efficient than this one. So yeah, but these observations may lead to different, I mean, you may improve your initial algorithm if it's possible, but it really helps to start with observing, trying to observe certain properties about the problem at hand. All right, so we will talk about this problem next week in detail. So yeah, there are other problems. Yeah, so this is the convex solve. This is given in the next slide. There are other problems in which the input is the same thing. For example, you may be given the same set of 2D points as input. Now the problem will be to find the triangulation of those, like this. Okay. In other words, connect these in such a way that they will form triangles. Okay, and the edges will not cross each other. For example, I don't want to draw an edge between this one and this one because it will cross all these triangles. This is called the triangulation of a point set, and it's especially useful when these points are in 3 dimensions. Imagine you have a 3-dimensional scanner in which you want to generate a model, a 3-dimensional model of some sculpture, some objects. Okay. And your 3D scanner basically generates a point cloud if you scan your object. And that point cloud, in order to be able to visualize it as a closed form mesh, it makes sense to triangulate those points. So point set triangulation is a really important problem that is in modeling area. And we will see that this problem actually is a dual of the Voronoi diagram. So where do we have it? So this is for the same point set. We can also have the Voronoi diagram, which is actually a dual of triangulation in the sense that look at this diagram. It's really interesting because some of the regions are unbounded. The region corresponding to this point goes all the way to infinity this side. I can bound this into some bounding bugs if I want. This is actually for practical reasons. We will do that actually. We are going to bound this Voronoi diagram with some finite bugs. But as you can see, the Voronoi diagram is really interesting. Its vertices, these are the vertices of the Voronoi diagram, are not one of the input points. This vertex here, why is this a vertex? Because it's equidistant to these 3 input points. So by the way, what's a Voronoi diagram? It's a diagram such that it shows the nearest site to any given point on the plane. For example, for all the points on this region of the plane, the closest of these blue points is this point. Okay, so for example, if you're here and if you wonder about which of those blue points, they may be post offices, for example. This is also called the post office problem, locating the nearest post office depending on where you are. So if you're here, the closest post office is this one. If you're here, the closest post office is this. If you're here, the closest post office is this. So without going over all of the post offices one by one, if you know which region you're in, you're immediately closest to the site that belongs to this region. So this is the Voronoi diagram. As you can see, it looks really like some biological or some natural shape. And in nature, this really happens. So for example, if there are competing things that are about these regions, that they will end up at these boundaries. For example, this edge, it's an edge because it's equidistant to this side and this side. And this vertex is equidistant to 3 or more sides. That's why it's a vertex. So we will see how to compute Voronoi diagrams. But one interesting property is that if you just connect 2 neighboring sides on the Voronoi diagram, for example, look at this Voronoi cell of this side. It's neighbor to this side, this side, this side, and this side. If you just draw line segments to your neighbors crossing the edges of these Voronoi diagram. If we just draw these edges, it will give us, yeah, it's seen in this figure better. It's going to give us the triangulation. This is the Delaunay triangulation of the same point set. So they are dual problems in that sense. Yeah, the sizes of these regions are determined automatically. It depends on the number and also the location of those blue points. Okay, so the size, for example, the size of this region is really determined by the location of these other points, the location of the other points. So given a set of blue points as input, a unique Voronoi diagram exists. All right, and sometimes we will also, when we come to this chapter, we are first going to prove that, for example, given a set of points like this, all these Voronoi cells, they are convex shapes. They may be unbounded, but they are always convex. We cannot have concave. A concave shape is something, I will talk about concave and convex shapes in detail in a couple of minutes, but we will prove these properties of the Voronoi diagram. But the size, its location, its shape, everything is uniquely determined by these locations and the number of these points. For example, if all the points are horizontal like this, let me just get a new figure here. What if the inputs, let me just increase this and get some blue points. All right. Okay. Oh, it didn't become blue. Okay. Oh, it doesn't. Oh, it's so very dark blue. Let me just erase. Let me just have some light blue here. Yeah, it's better. Okay, look at these blue points. Okay, so I can have my input like this. What if the points are on a horizontal line? What do you think the Voronoi diagram is going to look like? You can write in the chat box if you have any ideas. Let me get back to smaller pen size, 4 points, and let's get back to black. Yeah, exactly. They will be parallel lines. Very good. So here there will be no vertices, so they will be. I can actually have a line here also. Let's see, but I'll just draw it. You get the idea. Okay, so there will be parallel lines passing through the midpoints of these blue points. I mean, I cannot, if I draw them on the board, I would draw this bad. So sorry, my drawing is not that good. It's not that I'm using a mouse or on the computer. Even if I was drawing this on a blackboard with chalk, it would be as bad as this. All right, so but the main purpose is not to have good nice looking pictures, but to just get the idea across. So this is how the Voronoi diagram is going to look like: parallel lines passing through the midpoints of these points. So they will all be unbounded regions, but when they become collinear, this is what happens. But when the collinearity disappears, we will have some vertices of the Voronoi diagrams, and we will talk about this in after the midterm, probably at the mid-semester. We will talk about this in chapter 7. All right, so these are some interesting problems that we will be talking about in this course. We will have, look at this polygon. This is a simple polygon. It doesn't look so simple, but a simple polygon is a polygon. This is a concave polygon, by the way. A simple concave polygon is a polygon with no edge crossing, a connected, which means there are no holes in it, non-self-crossing. And for example, given a polygon like this, can you figure out how many cameras would you need for this one to cover the entire entire area of this polygon? Where to place the cameras? That's an interesting problem that we will talk about in chapter 3. All right, now let's get back to the geometric preliminaries. And I will start with the simplest ones, which are the points and vectors. All right, so let's get the new one. All right, so a point is the simplest two-dimensional object that you can have. And in order to represent a point, we need a coordinate system. So a point is represented by two values, it's xy coordinates. I can have it here. Okay, so it's going to have x, y coordinates. Let me make it bigger, or maybe I can decrease the font size, but yeah, for you to see better. So a point is something with xy coordinates. Okay, and in order for these coordinates to make sense, we need a coordinate system. For example, if the coordinate system, basically is going to be, let me flatten my image. Okay, the coordinate system is basically two axes that are orthogonal to each other. By convention, the axis that goes on the right is the x-axis, and this is the y-axis. This is the most frequently way we use the 2D plane, and we use the coordinates, but it could be anywhere. I mean, I could just describe x-axis to be this and y-axis to be that. All right, this is also a valid coordinate system. But if I do it like this is x and this is y, I may not have a right-handed coordinate system. It may be a left-handed coordinate system. All right, so in right-handed coordinate system, when x is to the right, y, positive y is towards up, and z coordinate is towards you, out of the screen. Just think of this z orthogonal to these x and y with 90-degree angle coming out of this screen. That's the right-handed coordinate system. We won't be dealing with 3 dimensions in this course, but the z coordinate is going to come up when we talk about the cross product, because the cross product of two vectors on the plane is a vector outside the plane. It's a vector. If I cross product two vectors, xy and x1, y1, the resulting vector will be something like this, 0, 0 with some z coordinate. All right, it will be a 3-dimensional. It will be a vector with no xy components, only the z component, and the z will sometimes be pointing towards you when it's greater than 0, and it will be less than 0 if it's pointing towards the screen. Okay, so in the negative z direction. So this is negative z direction in a right-handed coordinate system. And we will be using right-handed coordinate system in this course as well. So yeah, points are our basic entities. In addition to the axes, actually, in order, for example, if I ask you in this coordinate system, so I give you the x and y axes. Can you guess the values of this x and y for this point? The answer should be no, because I also need another thing, which is what is the unit vector on this x-axis? How does it look like? If the unit vector on this axis is this, which means that this is the coordinate 1, 0, we will have the unit vector with the same length on the y-axis, 1, 0, like this. So given if this is your unit, then now you can guess what this x and y can be by just measuring how many of these you need in order to get to this point. Okay, so 1, 2, 3, 4, 5. It should be like 6.1 something. So x here is something like 6.1, and y can be how many of these you need to get to here, maybe. Yeah, it's maybe 3.2. Let's call it 3.2. Now we have ourselves, after we have a coordinate axis like this, x and y, and a unit vector on these lines, we will have our point. Now, another thing is that this, if you look at this tuple, 6.1, 3.2, it's actually a two-dimensional vector. Okay, in terms of objects go, I mean, this is an order, this is a vector, right? I mean, for the x coordinate, I have 6.1, this is 3.2. As a mathematical object, this is a 2D vector, which means that I can use this when I tell you something about 6.1 and 3.2. You can use it as a point, as a position. You can use this 2D vector to represent the position in 2D space. You can use this vector also to indicate a direction and magnitude in 2D space. Okay, 2D vectors, their semantics could change from context to context. I mean, there's the same thing, 6.1, 3.2, as I said, it could be sometimes considered as a point, as a location, to indicate a location, but sometimes it will just indicate a direction and magnitude because it's a vector. Okay, in that sense, the direction and magnitude it actually shows is this direction with this magnitude. This is that vector from 0, 0 all the way to this point. If you draw this vector, this is the magnitude of this vector. The length of the vector is denoted by this, with 2 bars around it. This is going to indicate the length of this vector, which is found by squaring this, squaring that, summing them up, and taking the square root. So it's basically the distance, Euclidean distance of this point to 0, 0 is the length of this vector. You can just use the Pythagorean theorem to do that. We have a right angle here. This is the hypotenuse. Okay, so this is the length of the vector, and it's also given a direction. By the way, if I use it as a vector, it means that this vector does not have a position in space actually. I can draw this vector any place I like. If this vector has the same length and same direction, if I was able to draw a parallel line segment to this one with exactly the same length, it's still the 6.1, 3.2 vector. All right, these two vectors are not different if its length and its direction is the same. Vectors do not have positions in 3D space. This is in 2D space. Okay, so this is very important because this will be confusing when we talk about polygons. So when we come to polygons now, let me get a new whiteboard. So the polygon will simply be given to us as a list of vertices. Okay, so let this be a polygon. A polygon, the way it's given to us as input, will be a list of its vertices: v1, v2, v3, v4, v5. Sorry, this is v5, not 6. v5 and v6. So this is a hexagon. Hexagon is a polygon with 6 vertices, and this hexagon, this v1, v2, v3, they will be given as positions to us, so they will be points. So I will have this v1 will have some xy coordinates. Okay, now v2 also has some xy coordinates. Now I can consider them as points, but when I use some vector algebra on them, for example, given 2 vectors, now I'm going to show you some operations on vectors, v1, v2, v3, all considering all these things. First of all, I can do things like this. I can subtract one vector from another. So subtracting one vector from another, you just subtract the corresponding coordinates. So v2 minus v1 is another vector, which is v2x minus v1x, comma, v2y minus v1y. So it's going to, you can just subtract or add vertices. If you add them, you can also, so whether you add or multiply, the respective coordinates are added or multiplied, v1x and comma, the same thing. All right, and you can do this in not only 2-dimensional vectors, in any n-dimensional vectors, the summation and subtraction is defined this way. So we can add vectors. So what does it mean semantically when you do v2 minus v1? Okay, on this polygon, v2 minus v1 will be this vector. All right, it's going to be, as you can see, it tells me the length. By using v2 minus v1, I can actually compute the length of this edge. If I take the magnitude of this vector, it will tell me that this is an edge vector. Let's call it e1. Okay, this E1 edge will simply be V2 minus V1. But when I say edge vector, in this information, if V2 minus V1 is equal to E1, if I define E1 like that, in that sense, E1 will not have any location in 3D space. I lose that information as soon as I just save this information for E1. E1 will only have a direction and a magnitude. So E1 actually could be here. This is also, I mean, if it's parallel to this one and it's the same length, I could have E1 in any place. So vectors could be moved anywhere. They are just directions and magnitudes. So you need to be very careful about this. At this point, when you just save E1 as this, its location in 2D space on the polygon is lost. In order to be able to do that, I need some additional entity. I mean, if you want to save it as a line segment, if this is a line segment in 2D space, it will have a position. Line segments do have positions. So in order to do that, I need to store at least two vectors. I need to, if you also store its starting position, this vector starts at this point in 2D space and goes in this direction, then you can position your vectors in 2D space. So for example, if you want to represent this edge and its position on 2D space, for example, if you want to generate a point on an edge like this, for example, let's look at this point P. I want to generate this point P on this edge of this polygon. The way to do that is to form a line equation, which we call a parametric line equation, like this. Any point on that edge, let's call it PT, is simply could be formed by V1 plus E1t. Okay, so it's this simple. So there's a parameter here, t. When t is equal to 0, as you can see, it gives you, this is just, what is this? Look at the right-hand side of the equation. Multiplying a vector with a scalar. T is the scalar here. V1 and E1 are vectors. So then another operation you can do with vectors is multiply them by a scalar. It's basically scaling a vector. So if you multiply E1 with t, every individual element will be multiplied by t. Okay, every individual coordinate will be separately multiplied by t. This is what scaling a vector means. So if you look at this equation, it's very simple. Let's just say start at V1, go in E1 direction, and t is your main unit parameter. When t is equal to 0, you will be at V1. What happens when t is equal to 1? When t is equal to 1, you will be at V1 plus E1. What is V1 plus E1? It's V2, right? E1 is V1 minus V2 minus V1. If you add V1 to this one, you get V2. So at t is equal to 0, you are here. At t is equal to 1, you are here. So this becomes a parametric line equation. I mean, you can, if t goes from minus infinity to plus infinity, you would be actually representing this extension of this edge going all the way to infinity. All right, you can actually use this to define a half space. Any line that is oriented from some beginning location to some another point. So when we talk about line segments and lines, we will also give them to you as ordered, as oriented lines from one direction, from certain direction. For example, if I just give you a line like this with no order, the left and right of this line unordered is not defined. But if I tell you this is a line going from this point, point A to B, okay, then left and right is uniquely defined for such ordered lines. Just imagine yourself that are walking on this line. This part is going to be the left, this part is going to be the right of that line. And it doesn't matter whether the line is horizontal or vertical. I mean, for vertical lines, left and right are uniquely defined. Okay, if I have this order, as you can see, your left and right changes. Just imagine yourself. This left and right is not something global. is relative to the line segment. So just imagine yourself walking on the line. Left and right is always uniquely defined. Even if you have a horizontal line, you may argue that, oh, there's no left and right here. There's only up and down. But if I tell you like this, now imagine yourself walking on this line. Oh, okay, this is left, this is right. If imagine yourself walking on this line, this way, this is left, this is right. All right, so we will have our line segment and lines oriented like this. So there will always be some left and right uniquely defined. And why is this important? It's important to ask lots of interesting queries, like to determine whether a polygon is convex or not, to determine whether a point is inside a convex polygon or not. We will be using this left and right of line segments. So this will bring us to the next operation on vectors, which is, so we have seen how to scale a vector by multiplying with a scalar. We have seen adding and subtracting two vectors. And now we come to multiplication. How do we multiply two vectors? There are two different multiplications that are defined on vectors: the dot product and the cross product. Okay, so dot product is sometimes called the scalar product or inner product, linear product. The result is a scalar. It's simply you simply multiply the x coordinates, y separately, and you add to them the multiplication of the v2. This is v1y multiplied by v2y. Okay, so these are just scalar multiplications. So this is v1x multiplied by v2x, add to that v1y multiplied by v2y. So this is called the dot product between two vertices. It's used in machine learning in the form of cosine similarity between two vectors, two high-dimensional vectors. Even if you have very high d-dimensional vectors, which are in very large dimension, the dot product actually gives you the cosine of the angle between them. So if you have two vectors, v1 and v2, the cosine law says that the dot product between these two vectors, which you can compute simply by this, is equal to the cosine of the angle between them times the length of those vectors. So if those vectors are already unit vectors, if their lengths are 1, both of them will be 1, and their dot product will immediately give you the cosine. But if their length is not equal to 1, the cosine alpha multiplied by their length will give you the, simply if your goal is to get the cosine, just divide by their length and you get the cosine. So you can erase this part. So the cosine of the angle between them is dot product divided by their length. So this is something useful, and it's used in machine learning because if two features or parameters are pointing in the same direction or similar direction, the cosine of the angle between them is going to be small, and therefore the cosine alpha is going to be closer to 1. If two vectors are pointing in opposite direction, 180 degrees, the cosine of that angle is going to be closer to -1. So this cosine similarity is something that ranges between -1 and 1, and it tells you whether something is positively correlated or negatively correlated, or if the angle between two vectors is 90 degrees, the cosine is going to be 0. It also tells you that those two features are totally unrelated or so. Okay, so this is the dot product. Now I'm going to talk about the cross product, which we will be using more than dot product in our intersection test. We will be using it for intersection tests. We will be using it for point polygon inclusion test to determine whether a polygon is convex or not. So it's very useful. So here's how it's defined. V1 cross product V2. There's a formula for this, but I never memorized the formula itself. I always use this technique to find the cross product, which is this. It will give you a vector that lives in 3 dimensions. So it's the determinant of this 3x3 matrix. V1x, V2x, I have 0 here. There, sorry, not v2x. Sorry for confusion. So I write the components of v1 here, v1y, v1y and 0, then v2x, v2y and 0. So basically what I do is I write the unit vectors on x-axis direction, y-axis direction, and z-axis direction. So in other words, I is simply 1, 0, 0. J is simply 0, 1, 0. And Z is simply 0, 0, and 1. Okay, so these are, so I, J, so this is J and this is K, not Z. So this is J. I, J, K are these vectors in the Y direction, K is in the Z direction. All right, so these are unit vectors, and these are scalars, as you can see. So the determinant, in order to find the determinant of a 3 by 3 matrix, the technique that we use is something like this. We cross out every column and row, every row and column one by one. For each of these elements in the first row, it's going to be equal to I times, so I times something. I times the determinant of a 2 by 2 matrix. So when you say I times, you cross out the column here and the row here, all right, which is going to give you v1 times v1y times 0 minus v2y times 0. Since both of them are 0, it will be a 0 here. Okay, so then we come to J. We cross out these rows and columns. I have v1x 0, v2x 0. So it's going to be, so this is 0 and minus j times 0. And then finally we are going to have plus k. The only thing that you need to remember in this determinant is you need to go plus minus plus minus. So add, subtract. So this I is added, the j component is subtracted, k component is added. So when you come to k, what we have here is that v1x times v2, sorry, this is not multiplication, it's subscript, v1x times v2y minus v2x times v1y. So that's the formula many people memorize as the two-dimensional vector cross product, but I don't have this in memory, so I use this technique to get the formula. The good thing about this technique is that even if the third dimensions, it also works for three-dimensional vectors. If this is v1z, it will have I and j components as well, if the vectors have their z components. Okay, now this becomes the result, the cross product becomes a vector that's like this, 0, 0, and let's call this entity here z. Okay, so it will be a vector like 0, 0, z. Okay, whatever, since this k was 0, 0, 1, I multiply this k with this entity here that I measure, and it will be a vector like 0, 0, z. And in most of the problems we deal with, we will be interested in this value z in two point of views. The first is we will be interested in its sign, whether it's positive or negative, because v1 cross product v2 is not equal to v2 cross product v1. It's not commutative. Unlike dot product, cross product is not commutative. You will get a vector in the exactly opposite direction if you do v2 cross product v1, which is going to give us lots of hints in different problems. And the magnitude of this z, I mean the absolute value of z, is going to give us the area of the parallelogram formed by these two vectors. So let me just get to a new slide. It's going to be like this. If I have two vectors like this, I just form a parallelogram by going parallel to this vector and exactly same length. And this is the other vector. Okay, so the area of this parallelogram is equal to z. But Yeah, exactly. The area is equal to this the absolute value of z. Now, if you want to figure out the triangle's area followed by the two vectors form a triangle. So the triangle's area simply will be what after you take the cross product divided by 2, you will get the area of the triangle. Another good thing is that if this angle between these two vectors is alpha, the sine of that alpha is going to be equal to the z component of the cross product. So v1 cross product v2 z multiplied by again the lengths. I need to normalize it because sine is also between -1 and 1. All right, so we need to, if the vectors are not unit vectors, we need to normalize them, or we need to divide them. If you, sorry, I wrote it incorrectly. So the sine is equal to this. Okay, or if other, I mean, or I could have this v1, their lengths to this side. Sine alpha multiplied by their lengths gives me the z component of the v1 cross product v2 if they are two-dimensional vectors. All right, so now let's, I will just now show you some applications of cross product. After we know that, one very good application is that if I have a line like this from A to B, I can distinguish between these 2 points, whether they are on the left-hand side or on the right-hand side of this line segment. So P1, and I will do it like this. Look at these two vectors, P1 minus A and P2 minus A. Okay, if I cross product them with B minus A and cross product this with B minus A, the signs of these cross products, z components, are going to be different. For example, let's look at this one. P1 minus A is this vector, B minus A is this vector. In order to predict the sign of the cross product, you can use the right-hand rule, which is like this. If I want to multiply P1 minus A with B minus A, I draw the angle from P1 minus A to B minus A, and I try to use my right hand's 4 fingers to trace the angle. All right, if you trace the angle from that one of the vectors to the other vector with your 4 fingers using your right hand, because we are using a right hand coordinate system, your thumb, the direction of your thumb, tells you the direction of the resulting cross product, which actually is towards you, right? If you do it this way, it's towards you, meaning that that's positive z-axis. So if you do the cross product result, the result of this, the z value is positive. Okay, if point is on the right hand side, we should get something positive. If you do the same thing for this vector, try to cross product P2 minus A with B minus A. Again, draw the directed angle from P2 minus A to B minus A, and try to trace it with your 4 fingers, and you'll see that your thumb is this time pointing in the reverse direction towards the screen, which means towards negative z-axis. Okay, so we can use cross product to figure out whether a point is on the left-hand side or right-hand side of something. Now, we can use this our observation to solve the first application. Given a convex polygon, figure out whether a point is inside. This is point 2, this is point 1. Given a point and a convex polygon, figure out whether the point is inside the point polygon or not. So inclusion tests. We can use this for inclusion tests. A convex polygon is nothing but actually the inside of this convex polygon, the area is actually can be considered like this. It's the intersection of half planes. Have you ever thought about a polygon like this, especially a convex polygon, not concave polygons? Concave polygons cannot be thought as intersection of half planes because intersection of half planes, it's always convex. So what half planes are we talking about? The half planes we're talking about are this. Consider every edge. Look at look at the edges: E1, E2, E3, E4, E5, E6. So it has 6 edges. All right, so it's another hexagon. Oh no, there's 7th edge. I forgot this edge. So there are 7 edges. So consider the infinitely extended lines of all these edges. And also, when we talk about polygons, we need to consider ourselves direction of the vertices that are given to us. The vertices can be given to us in counterclockwise order, sometimes abbreviated as CCW. So counterclockwise, the clock goes this way, so this is counterclockwise. Sometimes it may be given to you clockwise. Whatever the direction is given to you, it should be indicated in the question or in the problem. It should be indicated. So if we are given counterclockwise ordered vertices on a polygon, consider the edges that are ordered with the same order as the vertices. So these will be my ordered edges. All right. These ordered edges, as you can see, there are also ordered lines if you consider the extension of these edges. Now, consider each edge is something like this. An edge of a polygon has this information. It says that to my left is the inside of the polygon. To my right, it's the outside of the polygon. Every edge actually says that. Look at this edge. This edge says the only thing I know is left of me is inside. All right. For example, for edge E2, even this place is inside. For edge 2, this is also inside. This is inside because edge 2, with just the information edge 2 gives us, all of this half space, half plane to the left is inside of the polygon. All right. A polygon, a convex polygon itself, is actually the intersection of all these information. If you intersect all the half planes that says, okay, this part is inside, this part is inside, this part is inside, this part is inside. So if you just intersect those half planes, you get yourself this polygon. All right. Now, this tells us, we have now an algorithm to figure out whether P1 is inside or not. In order for P1 to be inside, it has to be on the left of all of these edges. So I will make this cross product between E1 is just V2 minus V1 and this. So I will make this cross product, then I will make the other cross product. Okay, so by having P1 minus E7, whether this is V1 or not, P1 minus V1, P1 minus V2, P1 minus P3. So for every one of those, P1 is going to remain. For example, look at this vector here. This is P1. And when I do the cross product again from this one, all of the time it should be we should get negative z values. Okay, it should be on the left hand side. If the cross product that I do is, for example, P1 minus Vi cross product EI. If you do this, for example, you will always get negative values for all of the edges. If any one of them is positive, it means that for that edge, your point is outside the half space, which means that it's totally outside the polygon. Okay, so we can use cross product for inclusion, exclusion tests. Another thing of cross product is to figure out whether a polygon is convex or not. Okay, look at this polygon, which is not convex, it's concave. Now it's a good point to talk about convexity and concavity. In a convex polygon, any 2 points selected inside the polygon, if you connect them with a line segment, the line segment is going to be entirely inside the polygon. In a concave polygon, on the other hand, for some points like these, if you connect them with a line segment, part of the line segment, as you can see, is outside the polygon. Therefore, it's not convex. All right. So how can we use the cross product rule to determine whether we are in a convex polygon or not? Again, we are given edge directions like this, directed edges. So any ideas from you? You can write in the chat box, or you can turn on your microphone if you want to answer this question. So can I use the tool I have, the cross product, to determine whether a given polygon is convex or concave. So there's a hint here. I mean, look at this part is like gives the concavity, right? What happens in this part of the polygon? Which vertex just destroys the convexity? Yeah, again, the signs of the cross product should be the same. Yeah, you're right. That's actually the same idea. So just think about yourself walking along a convex polygon. What happens at every vertex? So that's the correct answer. The signs should be the same. So what happens is that every time you're walking on a convex polygon in counterclockwise direction, at every vertex, you steer your wheel to the left. Okay, you're always making left turns. Look at this. Come here, make a left turn. Come here, make a left turn. Make a left turn. Make a left turn. Just you're going. A convex polygon is just like a circle that you go in a certain direction. You're always making same left turns. What happens here is that, okay, this is a left turn, left turn, left turn. But look at this. From here, the left turn should be somewhere on this half space, but we are doing a right turn at this vertex. So this vertex destroys the convexity. Okay, so and whether you're making a left turn or right turn is basically asking whether the next vertex is to the left of this edge or to the right of this edge. The same test we did for inclusion. If the next vertex, considering an edge, considering this edge for example, if the next vertex, in order for convexity to hold, the next vertex should be on the left hand side of this edge. It should be somewhere here. Okay, if it's above here, it means that it's on the right hand side, and now we destroyed convexity. All right, we are going to be using this when we talk about convex hull algorithm. By the way, a question: what happens when the z turns out to be 0? You do the cross product, and the result is 0. Why is when can this happen? I talked about z can be negative, z can be positive, but when can z be 0? No, I can still have a closed shape like this. Let me have a polygon to you. Okay, these are the vertices. Now I will show you a case where z is 0. Let's have another vertex right here. Yeah, exactly. When they're collinear. As you can see, if 3 points are on the same line, they're collinear. Z in this case is going to be equal to 0. For example, look at this edge. Considering this edge, the next vertex is neither on the right hand side nor the left hand side. It's exactly on the line. In that case, z is going to be 0. These 3 points will be collinear. As you can see, it doesn't destroy convexity. So when I'm checking whether a polygon is convex or not, I can have in my if statement, if z is less than or equal to 0, then it's still convex. All right, because less than 0 means it's on the left hand side if I do the multiplication like that. So if for all of the polygon edges this holds, then it's a convex polygon. Otherwise it will not be convex. All right, so we used it for convexity check, inclusion check, and the final thing that I'm going to discuss today, then I will going to call it a day. We are going to finish our lecture for today and continue next week. The final thing I'm going to discuss is using cross product to determine whether two line segments, I'm given a line segment, another line segment here, and another line segment here. Okay, let's give them names, endpoints A, B, C, D, E, and F. Okay, so we are given 6 endpoints indicating 3 line segments. Uh, okay, since these are line segments, I cannot use intersections of lines. I mean, if you think about this AB, if you form a line from A to B or B to A, this line intersects this other line. Actually, since pairwise they are not parallel, there are no parallel lines here, all of them are going to intersect with each other, right? But I'm not asking about this. I'm asking about line segment intersection. For example, AB does not intersect with EF or CD, but CD intersects with EF. Now, can you tell me a rule to determine whether two line segments intersect or not? And a big hint is this is about cross product. So, which means that when I say this is about cross product, it's about things becoming on this side or that side. For example, what do you see about EF and AB that says they do not intersect? Uh, what what basically, I mean, we see it directly on the figure here. If both endpoints are on the same side of the line formed by EF, for example, AB is on the same side of EF. They are both on the left from F to E. If you have this line from F to E, A and B are both on the same side. If that occurs, they cannot intersect. But another thing, now look at this. For example, let's call this P and Q. Okay, P and Q are on different sides of A and B. If you look at P and Q and consider this line, they are on different sides. P and Q are on different sides, but we still don't intersect. The same was true actually at E and F. So the rule is basically for two lines to intersect, from both the perspectives of the line segments, the other 2 points should be on two different sides. For example, P and Q, here PQ and AB does not intersect because from the perspective of P and Q, A and B are on still the same side. Okay, so we are going to do two cross product checks, actually four cross products. One, from the perspective of PQ, I'm going to make this cross product Q minus P cross product A minus P, and I will also do B minus P cross product Q minus P. This will help me determine whether they are on different sides of this line. If they're on the same side, I can break out of this statement, if statement saying that they do not intersect. But after I do that, I will also, even if they're on two different sides, it doesn't guarantee intersection. In order to guarantee intersection, from the perspective of AB, P and Q should be on the other side, on two different sides as well. What I will do is, I will check this time whether P is on the left side of B minus A vector. Now I will look at the B minus A vector and cross product it with P minus A. Then I will check the cross product of B minus A with Q minus A if they are on different sides. And if they're on different sides in both cases, I have, if you have something like this, it means that from the perspective of this line, these 2 points are on two different sides. And from the perspective of this line, these 2 points are also on different sides. That's the necessary condition for two line segments to intersect. I mean, this is not the only solution, by the way. I mean, cross product, this is just an application of cross product to determine line segment intersection. But without using cross product, can you find whether two line segments intersect or not? Any other ideas? One thing that you can do is just form the line equations, intersect the lines. For example, let me get a new whiteboard. Okay, so in order to see whether these two intersect or not, I form the lines. I find the intersection of, if they are parallel, there's no intersection, but if they're not parallel, there will be an intersection point. After I find this point, since I have a parametric line equation, for example, from t is equal to 0 to t is equal to 1, okay, for this parametric line, for example, if this point P happens to be outside 0, 1, because after I find this intersection, which means that I also know the parameter intersection of this intersection point P, I will know this parameter. If it's less than 0 or if it's greater than 1, it means that there is no intersection. Okay, as in this case, for example, the intersection occurs at P in which T is greater than 1 here. In that case, it's outside the boundary of this line segment and hence no intersection. So that's another alternative method to figure out whether two line segments intersect or not. All right, so we will talk about circles, some creating circles from 3 points, whether finding a point is, whether a point is inside a circle or not, or the closest, the distance of a point to a line. Okay, so finding this distance, things like that. So we will talk about this next week. So that's all I want to talk about this week. We have talked about a lot of preliminary things. We've talked about line segments, polygons, polygon inclusion, tests for convex polygons, dot product, cross product, and I will talk about planes, half spaces, and we also did this convex test today, and some circles next week. All right. Any questions before I finish today's lecture? I guess no questions. All right. Thank you all for attending. I will post these videos along with the chat transcript. Again, I will edit the chat transcript to include only the course-related material on YouTube as unlisted videos. So only the people who have the link will be able to access these. And I will post the links on OttoClass. All right. If you have any questions afterwards, please feel free to send me an email. Thank you. See you all next week. I will stop sharing my screen. I will stop recording